Hi, I'm Matt Young, an assistant professor in the Department of Mathematics and Statistics at Utah State University. In this video, I'll give you a short overview of my research program. By training, I'm a pure mathematician, but most of the problems I'm thinking about are coming from mathematical physics. The typical way in which I find a problem is by first discussing with physicist colleagues to understand the types of problems they're thinking about, and then translating this into a problem in mathematics. The typical tools which I then use to solve this problem are coming either from algebra and representation theory or geometry and topology. The problems which I find most exciting are those which aren't solved using any one of these three tools on their own, but rather can only be solved when using all of these tools at once. In this way, if I can prove a theorem about algebra and representation theory, I can learn something about geometry and topology, okay? And vice versa. One concrete problem on which I'm currently working is the mathematical construction of topological quantum field theories. These are toy models of physicist quantum field theories, which are mathematically tractable. Part of the interest in topological quantum field theories is their amazing applications to topological phases of matter and quantum computing. The diagram here illustrates on the top a topological isomorphism, which when translated using the language of quantum field theory corresponds to the algebraic inequality below. Okay, so this is an example of using topology and geometry to learn something about algebra. A second project on which I'm working is understanding hidden quantum group symmetries in the BPS state counting in quantum field theory. A priori, this is an extremely geometric problem about, well, understanding somehow concatenation of surfaces, but using the technique of Hall algebras, I translate this into a much more tractable algebraic problem. Studying this algebraic problem, we then learn about the original geometric problem. A third project I'm working on is to understand the emerging area of what I'll call higher categorical representation theory. In the same way that representation theory aims to understand symmetries of objects, higher categorical representation theory wants to understand symmetries and symmetries between symmetries and so on. The diagram here illustrates an important algebraic object in this theory, that of a modular tensor category. All of this work that I described here, I'm carrying out as part of the Pure Mathematics group at Utah State University. This is an active group with a number of faculty members and a group of graduate students. And it's a great place to learn and do mathematics. We have a weekly seminar where the group gets together, learns a new topic together, or discusses a new research result. If you have any further questions about what you saw in these slides or about my research, please feel free to contact me at the email address on my webpage. Thanks for your attention.